All right, here's your project, flipping Ferraris. It really has to do the math behind how quickly a vehicle can brake, knowing how fast you're going. So when people first learn to drive, they're often told that the faster they're driving, the longer it'll take to brake or to stop. So when you're driving on the freeway, you should leave more space between your car and the car in front of you when you're driving faster than slower through a neighborhood. Have you ever wondered about the relationship between how fast you are driving and how far you travel before you stop after hitting the brakes? Think about it for a minute. What factors do you think might make a difference in how far a car travels after hitting the brakes? So let's just talk about a few of them. One is the weight of the vehicle. The heavier it weighs, the longer it'll take to stop. Another factor, speed of the vehicle. The faster you're going, the longer it'll take to stop. Another factor, the road conditions. If it's wet, icy. How about the condition of the tires? Are they worn out? Do they have a good grip? That's friction, right? A part of it. How about the condition of your brakes? All of these contribute to how quickly you're going to stop. So how much the vehicle weighs, the speed the vehicle's going, the road condition, the condition of the tires, and the condition of the brakes. There might be another one I'm not thinking of. There's actually been quite a bit of work, I'm sure, done by places like Michelin and stuff, that the relationship between the speed of the car and braking distance. So imagine your car to be this Ferrari, a super fast car. So experiments have shown that on smooth, dry roads, the relationship between the braking distance and speed is given by this equation. Speed is given in miles per hour and the distance is in feet. So how many feet should you leave between you and the car in front of you if you're driving the Ferrari at 55 miles per hour? Just see. So the equation is d at s equals 0.03 s squared, and what you're given is the speed. So where there's an s, so plug in 55, so d at 55. It's okay to use a calculator. That's what I'm going to do. So 0.03 times 55 squared. So that's 90.75 feet. And then write a sentence. Like, you should leave 90.75 feet between you and the car in front of you. Okay, what distance should you keep between you and the car in front of you if you're driving at 100 miles per hour? So now I'm going to plug in 100. 0.03 times 100 squared. And that answers 300 feet. C, if an average car is about 16 feet long, about how many car lengths should you have between you and the car in front of you if you're driving 100 miles per hour? So about how many is, we're just going to round to a whole number. So if you're going 100 miles per hour, we just said we needed 300 feet. So how many 16s are in 300 feet? So that's about 19. So you need about 19 car lengths. When traveling 100 miles an hour, which you should never do. That's way past the speed limit. License, be suspended, vehicle impounded. Innovate. Says it makes sense to a lot of people that the car is, it makes sense to a lot of people. If the car is moving at some speed, then goes twice as fast, then the braking distance is twice as far. Is this true? Explain why not? So these go, no, not true. And I'm just going to use the examples we did. We just did at 55 miles per hour, you need, what was it, 90.75 feet. A 100 miles per hour, which is like less than double 55, you need 300 feet. .300 is more than triple 90.75. So graph the relationship between speed and distance below. So one is going to be the speed you're going, call that S at t, and the other is going to be the speed, let's call that S, sorry, and then the other one's going to be the distance that you need going at that speed. I'm going to count the squares. So if I'm going up to 100 miles per hour, let's just see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6. So I'm going to count by twos. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. All right. I'm going to assume that it's similar. In fact, it's probably even taller up here. It probably goes up to like 20-something, 30-something. So we're going to count and realize what I'm looking for. So 0 would be 0, just so you know. So remember, I'm graphing this, 0.03 s squared. So we already know at 55 you need 90.75, and here you need 300. So that's like about 20 or so. So if I go 300 divided by 20, so like 15 every box. So if every box, maybe every 2 boxes is like 30, then 60, 90, 120, 150, 180, 210, 230, 240, 270, 300. All right, so I'm going to plot the points that I know, and that's probably enough. So 0, 0 I know, 55 and 90.7. Estimate where that is. 100, we need 300. So there's my graph. Describe the math features that you see. What do you notice? Well, I notice it is increasing. I notice it's concave up. So increasing is like that the distance increases as speed increases. That's what that means. Concave up means that the distance is increasing at higher rates as it goes up. So it's not a constant. It's increasing and increasing as it's going up. So the faster you drive, the more distance you need. I notice it's a quadratic function, and that the 0.03, that there's a vertical compression on there. Those are the things I'm looking at. What if the driver of the Ferrari was cruising and suddenly hit the brakes to stop because there's a cat in the road? She skidded to stop and fortunately missed the cat. When she got out of the car, she measured the skid marks left by the car so that she knew that her braking was 31 feet. How fast was she going? So in this example, we know the distance, which is 31 feet, but we don't know how fast. So we're going to use this equation, but this time we're going to make it equal to 31 and then solve for s. So divide, so 31 divided by 0.03. And then the square root of that. So when I take the square root to both sides, I don't need positive and negative, just the positive answer. And so the answer is about 32. So how fast was she going? She was going about 32 miles an hour. Part C. If she didn't see the cat until she was 15 feet away, what is the fastest speed she could be traveling before she hit the brakes if she wants to avoid hitting the cat? So if she didn't see the cat until the cat was 15 feet away, what is the fastest speed she could be traveling before she hits the brakes? So 15 equals 0.03 s squared, that's the distance. Divide by 0.03. And then the square root. And we'll round it. So, if the cat is 15 feet away, the fastest speed she could be traveling is 22 miles per hour if she wants to avoid hitting the cat. Six, part of the job of police officers is to investigate traffic accidents to determine what caused the accident. In fact, I've seen that before when they go out and they have their little stick and they're measuring distances and doing some math to see what happened. They measure the braking distance using skid marks and calculate speeds using math relationships, just like what we saw here, but although they often use different formulas to account for other factors such as road conditions. So let's go back to the Ferrari on a smooth, dry road in this relationship. Create a table that shows the speed the car was traveling based on the braking distance. So, in other words, we're now going to switch the output and input. So we want to do a table of values that has a sense of the speed and distance. So now distance is like your x coordinate and speed is like your y coordinate. So we already have some of them, right? So we already said that if you're going 55 miles an hour, you need about 90.75. Said if you're going 100 miles per hour, you need about 300. We just did this one, right? So 22 is about 15. One we did before, 32 is about 31. So there's a table based on it. So can you write an equation then that gives the speed of the car was traveling for a given braking distance? So instead, can you do the inverse of it? So our original equation was distance is equal to 0.03 s squared. There it is. So how about if we inversed it? If s equals 0.03 d squared, could you solve for d? So step one would be to divide by 0.03. And then the second step would be to take the square root. Now we don't need positive and negative, so we'll just put a domain restriction to understand, just like for this domain, the range for this one went from 0. So this is going to go from 0 to infinity. It's not, and probably infinity is probably wrong in terms of the distance, but you get the idea. There's no negative numbers here. So s divided by 0.03, and then the square root of it. Now what would that graph look like if I did it? Now, if I'm going to do the inverse, I'm not going to try to recreate the wheel, so I'm going to go back here. So this scale then is going to be changed around. So I'm going to count to 100 along here. This is my speed. I'm just going to count by tens. And along here, remember we counted by 30s. Sure, I know which tick mark is which one here. Kind of stretched it out a little bit. But, so this last one is 300. So I know 300 goes with 100. I also know that 55 and 90 kind of go together. So there's 90 and 55. And of course 0 and 0. And now describe its features. Well, this one is still increasing. So, as distance is increasing, so is speed. But this one's not, this is concave down now. So as your distance is increasing, your speed actually is slowing down. So even though it's increasing, it's slowing down how fast it's increasing over time. This now is a square root function. In this square root function, when you divide by 0.03, you're dividing by a fraction. It's really times the reciprocal. So another way, 0.03 is the same as 3 over 100. So the reciprocal of that would be 100 over 3. So meaning inside, in terms of being multiplied, whatever that number is, the square root of that, there's now actually, it's being stretched. There's actually a vertical stretch in this sense. So like 10 over root 3 root s, that number in front of s is larger than 1. It's creating a vertical stretch. All right, turn the page. It says, what do you notice about the graph of s at d compared to the graph of d at s? What is the relationship between the functions? Well, I think I kind of gave it away. So, what do you notice about the graph of s at d compared to that? So, why don't we do this? So, s at d compared to d at s. So both are increasing. One is concave up. That was the original. The other is concave down. One's a quadratic. The other is a square root. They both have the same domain. And range. So what is the relationship? Well, s at d and d at s are inverses. They reverse each other. So consider the function d at s equals 0.03 s squared over the domain of all real numbers, not just the domain of this problem situation. How does the graph change from the graph of d at s in question number 3? So consider the function d at x over the whole thing. So how does the graph change from the graph of d of s in question number 3? So if there's no domain restriction, then our graph here would be reflected over on the other side, and you would see the full parabola. So this is what you have right now. You would have the symmetry on the other side. So it's still concave up, but now from negative infinity to 0, it's now decreasing. And concave, it's still concave up through everything. So from negative infinity to 0, it's decreasing, then increasing, it's concave up. The range does not change. It's still all the positive numbers above, just been reflected over on the other side. How does changing the domain of d of s change the graph of the inverse? Well, therefore there is no inverse with the full domain. What happens? It fails, doesn't it? What does it fail? Now, if we're just doing, if you had an inverse and it wasn't a function, you could think of the graph that we have. You know, this graph that we have, you could reflect it in that the full one would look sideways like that. But then it would fail the vertical line test and would be no longer a function. So, and that was the question here. So, if you decide to graph the whole thing, that's what it would look like. Is the inverse still a function? And the answer is no. And so why again? It fails the vertical line test. And you can see that the vertical line test fails here, the horizontal line test fails. All right, I'm proud of you. You have finished the project and thought through it mathematically. GMath, over now.